Hai, Assalamualaikum and selamat sejahtera. We are from Group 8, Group Bumi Lawang. Today I'm going to present our project presentation. The title of our project is Heat Transfer Analysis in a Shell and Tube Heat Exchanger. Okay, this is our group members. The first one is Muhammad Hafiz bin Sukur as a group leader. The material number is DD220009. The second one is Muhammad Amirul. The material number is DD220008. The third one is Ashraf, DD220014. The last one is Karinas, DD220010.
Assalamualaikum. My name is Muhammad Amirul. My metric number is DD220008, and I will describe the introduction of this project. For definition of heat exchanger is transfer thermal energy between two or more fluid without mixing them. Physical barriers like plates or tube separate the fluids, ensuring efficient and safe heat transfer. For the type of the heat exchanger is use the shell and tube plate. The application uses at the HVAC system for heating, ventilation, and air conditioning in building. The importance is the energy efficiency. By optimizing transfer, they reduce energy consumption and operational costs. For the heat transfer mechanism, for the first is for conduction. Heat transfer through direct contact in solids, driven by molecular vibration. For convection, heat transfer in fluid, liquid, or gases due to bulk fluid motion caused by temperature difference. And for radiation, heat transfer via electromagnetic wave, occurring even in a vacuum. So the scope of this study is to discuss and apply the uses of conduction, convection, and radiation formulas in the governing equation of the heat transfer. For now, we explain about the process description, about shell and tube heat exchanger system. For the working principle, the fluid flow, one fluid moves through the tubes, the other fluid flows around the tubes within the shell, and fluid allocation, hot and cold fluid are assigned to the tube or shell side based on system requirement. For the pressure consideration, lower pressure fluid flow through the shell as tube can handle high pressure, and the shell fluid enter through the top inlet, and the tube fluid enter from the bottom right inlet. The main component about the shell and tube heat exchanger system, first is shell. For the outer casing, hold the shell side fluid. For the tube, inner pathway for the tube side fluid, and the baffle direct shell side fluid flow to improve heat transfer efficiency. The application of heat exchanger, first is steam condenser, convert turbines exhaust steam back into liquid water for use, and the cooling system remove waste heat from the system using cooling water.
Okay, this is the problem example for current scenario. If you look at here, this is a question of the shell and tube heat exchanger used in a power plant to cool down the high temperature steam hot fluid from 400 Kelvin to 320 Kelvin by exchanging heat with cold water entering at 300 Kelvin. The heat exchanger consists of carbon steel tube. The thermal conductivity given K is 50 with an inner radius is 0.01 and the outer radius is 0.015 meter. The tube length is 5 meter. Okay, the heat transfer process involve conduction through the tube walls, convection between the fluid and the tube surfaces, and the radiation from the hot tube surfaces. The convection heat transfer coefficient for steam is 800 and for water is 1200. Okay, the MACT given is 0.8. Okay, now I'm going to explain the calculation for the current scenario. There's divided by 4 parts. The first one is conduction, convection, radiation, and also the total heat transfer rate. Okay, the first one, if you look at the left side of the slide, we could see the Q conduction formula. So the first one, is conduction. The heat transfer through the tube wall occur due to thermal conduction. Using that formula, okay, the K given is 50. Okay, the R inner is 0.01, R outer is 0.015. The T steam or T hot is 400, and T cold or T water is 300. So just put the value in the formula, so we will get the Q conduction for the current scenario is 77481.21 watt. Okay, for the second or the middle side of our slide is the convection, referring to the fluid to the tube surface. You can see the formula there. The Q convection equal to HA times by T fluid minus T surface. Okay, the hot fluid steam, but H steam given is 800. The area is 0.314. The T surface is 250 and the T steam is 400. Okay, the value for Q convection steam is 12,560 watt, and it's different with the cold fluid, which is water. The H given is 1,200. The T water 300. T surface 350, and the area is 0.471. Okay, the Q convection for water is 28,260 watt. Okay, if you see at the right side of the slide, we can see the radiation formula for hot tube surface to the surrounding. The formula is there. The Q radiations equal by the sigma times by emissivity times by area, and times by T steam power 4 minus T water power 4. Okay, the sigma given is 5.67 times 10 to the power of negative 8, and the emissivity 0.8, and the area is 0.471. Okay, the Q radiation, the final answer for the Q radiation is 373.88. Okay, this is the continuous calculation for total heat transfer. If we look at the left side of our slide presentation, the Q equal to U times by A times by different temperature of LMTD. Okay, the A given is 0.471, T hot inlet 400, T hot outlet 350, T cold inlet 300, and T cold outlet is 325. Overall heat transfer coefficient U, we assuming it 150. Okay, if you want to find the total heat transfer rate, we need to find the temperature difference for T1 and T2 first. Okay, the different temperature for T1 is 75K, and different temperature for T2 is 50K. Okay, after that we need to calculate the different temperature LMTD. The value for different temperature LMTD, we got 61.66 Kelvin. Okay, the last one we just need to apply to the earlier formula. For the final value for calculate total heat transfer rate, we got 4,356 and to 8 watt or 4.36 kilowatt. Okay, next we move to improvement scenario. The equation given is the current shell tube heat exchanger uses a stainless steel tube, has a cold side mass flow rate of 0.02. The proposal is to enhance performance for replacing the tube material with copper, K given at 390, increasing the cold side flow rate to 0.03 to improve the convective heat transfer, and introducing the baffles to enhance turbulence in the shell side flow. Okay, the improved parameters, the first one we have the material, the copper, thermal conductivity, the K is 390, replace the stainless steel is 6.2. Okay, the side cold side mass flow rate 0.03, increasing the convective heat transfer coefficient on the cold side, H cold is 1072. The shell side convective heat transfer coefficient, we assume the H hot remains 1200, and the last one is tube dimension, the length 1.5, in the diameter 0.02, and the outer diameter 0.024. Okay, now I'm going to explain the calculation for the improvement scenario. Okay, in total we have 4 parts here. So the first part is improve conduction. Okay, if we look at if we see at the left sides of our presentation slide, that is the formula for the R conduction, and the final value for the improvement conduction is 4.538 times 10 power of negative 5 kilowatt. This is significantly lower than the stainless steel tube resistance Arcon steel equal 0.00108 kilowatt. Okay, at the middle we have improved convection cold side. Okay, that is the formula for the improved convection. The RO HO we have 800, the MU we have 0.03, and the MO we have 0.02. Okay, we just need to follow the formula and seek the value. Okay, the H nu we got 1106.53. Okay, for the third one, we have improved overall the heat transfer coefficient at the right side of our presentation slide. Okay, that is the formula for the improved overall heat transfer coefficient given for H hot for improved overall that improves. So we have the H hot at 1200, the H cool we have 1106.53, and the Arcon from the first formula is 4.538 times 10 power of negative 5, and the final value we got from the improved overall heat transfer coefficient is 552.01. Okay, this is the continuous calculation for the improved scenario. So the last one we have the improved heat transfer rate. Okay, that is the formula Q nu equal by U nu times A times different temperature LMTD. Okay, the U nu we have 552.01, the area is 0.113, and the different temperature LMTD we have 61.66. Okay, just put the value on the current the formula. We got the final value is 3846.17 watt. Now I'm going to explain the performance comparison between the current and improved scenario. There's in total 7 aspects. Okay, the first one we have heat transfer coefficient. The current scenario we have 150, and the improved scenario is 452.01. Okay, the observation or the impact from the improvement, we have increased in about 268% attributed to the use of copper tubes, high thermal conductivity, and optimize the fluid flow. Okay, the second one you have total heat transfer rate. The scenario we have the current scenario we have 4356.28 watt, and the improvement scenario we have 3846.17. Okay, this is the reduction of 11.7% due to lower different temperature LMTD, offsetting the benefits of the improved U. Okay, the third one we have log mean temperature different temperature of LMTD. When the current scenario is higher and the improved scenario is lower. Okay, reduce the different temperature of LMTD like caused by changes in operating temperature or fluid flow rates. And the last one, the fourth one, we have thermal resistance. For the current scenario, we have the higher or lower efficiency. The improved scenario we have the higher efficiency. So the impact observation from the thermal resistance is significant reduction in resistance due to the enhance of U and enabling efficient heat transfer with a smaller thermal gradient. Okay, next we have the energy efficiency. From the current scenario is moderate, from the improved scenario is higher. Okay, the impact or observation from the energy efficiency is improved design allows for better heat transfer at lower operating temperature, potentially reduce energy consumption. Okay, next we have turbulence or pressure drop. From the current scenario is lower turbulence or lower drop. For the improvement scenario is higher turbulence and increase the pressure drop. Okay, the observation is improved turbulence enhances the convection heat transfer by introduce additional resistance to fluid flow. And the last one we have overall system performance from the current scenario is moderate, but at the improved scenario is improved with the trades off. Okay, the observation from the overall system performance is improve the thermal efficiency but requires further optimization to fully balance the heat transfer rate and the system performance.
Okay, Assalamualaikum. My name is Muhammad Kharunas bin Wahid. I will present about discussion. So, key finding from the project that we study. First, have an improvement in heat transfer coefficient, which is increased significantly from 150 to 552.01, approximately around 268 percentage. This increment due to replacing the material, which is from stainless steel tubes with higher conductivity copper tubes, and also optimizing fluid flow rates. And second one, the reduction in total heat transfer decreased by 11.7%. It dropped from 4356 to 3846. This due caused by a smaller log mean temperature difference, which is LMTD, and also a potential adjustment in fluid flow rates or operating temperature. So impact of for this improvement, first, thermal efficiency gain. So the higher U, which is a coefficient heat transfer, indicate improved efficiency, and then allowing for better heat transfer at lower thermal gradients. And also, this improvement can lead to reduced energy consumption and also operational cost over time. Second one is challenges in heat transfer rate. So the need of balancing improvement in thermal efficiency. And then the last one, factor like increased turbulence, pressure drop, and change in flow pattern contribute to this reaction. So that's all. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ashraf Mashari and my magic number is DD220014. And today I'm going to present about the conclusion for the shell and tube heat exchanger. For the summary of the finding, the optimizing of heat exchanger design significantly improved in thermal efficiency and operational cost. And the second is the purpose of improvement such as a material upgrade and the flow rate adjustment enhanced the heat transfer efficiency by the 268% in demonstrating the effectiveness. For the recommendation, the further research and the advanced material composite for a better thermal conductivity, explore the innovative design such as a modular heat exchange or a smart monitoring system for enhancing the adaptability and the performance of the heat exchanger. And lastly is a conduct long-term performance testing under the various industry conditions for the reliable validation for the shell and tube heat exchanger.